Hello everyone and welcome to this presentation on logic gates. Okay, we're going to be looking at three key logic gates that we can use in our circuits or in our code. First one is going to be the AND gate, second one is going to be the OR gate, and then the third and final one is going to be the NOT gate. Now logic gates are typically used either in a circuit itself or in the code to make a logical decision. Now we've done basic stuff in the form of if questions, okay, but we can now combine those if questions so we can have two questions together and we can use what we call a logic gate to make a decision. This will make more sense as we go into the individual gates themselves, okay? But the most important thing is we can either have an IC logic gate, which is part of the integrated circuit, okay? So that goes into our actual electronic circuit, so we don't have to have a microcontroller, we can use an IC chip if we wish, or we can stick it on the microcontroller code and make that and or not logic inside our code. Okay, so first things first, let's just jump into the gates and then it will make more sense as I give you the examples of what we're doing. So the first thing is going to be the AND gate. Now, these gates have two inputs and one output. Input A and input B. These are going to be, say, our sensor readings that are coming into the AND gate. The output will be dependent upon those two values coming in on input A and input B. Now, the easiest way to do this with the gates is simply ask the question in the name of the gate. So for example, if input A and input B are true, then the output will be true. So we use that word and there. Now, if we look in the bottom right corner there, we can see that we have a logic table for the AND gate. If you have input A, input B, and then we have the output that results from those two inputs. You will notice with an AND gate, the only time the output will ever be true is if both A and B are true. Okay, so if they're both false, it'll be false. If one is false and one is true, it will be false. Otherwise, if they're both true, it will then be true on the output. So let's have a look at an example circuit that we might do. Okay, we're going to go back to our street lamps from last year. Okay, we're going to have a look at an AND gate with a street lamp. Now with the street lamp and with the IC for the AND gate on the left here, you will see that we have input A and input B. Input A is on pin number 2, input B is on pin number 1. We then have the output on pin number 4, or Y as it is labelled on that diagram there. Okay, we then have the VCC and the ground. That's standard in electronics. You have your power supply and your ground. Okay, now on input B or on pin number 1, we're going to have a low light sensor. Whenever the level of the lighting is low, that is going to output a high signal into this IC chip. So it's going to detect when the light level is low. We're then going to have what we call an RTC or real-time clock. Okay, now in this example, the RTC will be high when the time falls between 7 p.m. and 8 a.m. With an RTC, what we can actually get it to do, there are different types of RTCs, okay, but essentially what we can do is we can set a little time window on there, and that real-time clock will monitor the time. It'll normally have a battery built in as well, so that it continues to monitor the time even when the circuit is turned off. Normally a little like button battery or something. Okay, and that real-time clock will be able to indicate when it's between the time of 7 p.m. and 8 a.m. So it's going to run overnight, okay, for our street lamp. If we have a look at the logic on the AND gate then, during the day when the light level is high and it is, let's say it's 4 o'clock in the afternoon, okay, then the low light sensor will be low because it is a high level of light, okay, so that sensor isn't detecting a low light level. We then have the RTC. It will also be low because it is not between 7 p.m. and 8 a.m. Okay, so the output from that is also going to be low. So both A and B are going to be low, and therefore Y will be low because A and B is low. So the street lamp will be off. Okay, now let's say there was a storm coming in and the light level drops. Okay, so the low light sensor now goes high because the light level is low. Okay, the clock, it's still 4 p.m. The clock is still low because it does not fall between the 7 p.m. and 8 a.m. We have an AND gate on here. So low light sensor is high and RTC time is low. So the output of the AND gate is still low, okay, because A and B aren't high. Okay, so the street lamp stays off. When it passes 7 p.m, the RTC time will go high because it's within that time window. The low light sensor is still a storm. Okay, the low light sensor is still detecting low light, so both are high. A and B are high, and therefore the street lamp will turn on. Now let's say it is summer. Okay, the storm passes over. Okay, and the low light sensor now detects the light has gone bright, so it is now low because the low light sensor isn't triggered. Okay, so now B is low, A is high. Okay, so B and A aren't high. Okay, it's an AND gate, therefore the street lamp will turn off again. Okay, so both of those values need to be high in order for the street lamp to be on. If we look at the code implementation, so let's say we don't want to do it in the form of the electronic circuit, we can also do this in the code side on a microcontroller. We simply use the ampersands. Okay, so two ampersands together. The ampersand is on your number 7 key. Press the shift key and press 7 and you will get an ampersand. Okay, and if you look at there, we'll say if low light level sensor equals high and is time enabled equals high. So those two ampersands there combine those two questions together as an AND gate. The street lamp will turn on if they are both. So if the low light level sensor is high and the time is enabled, the street lamp will turn on, else the street lamp will turn off. So those two ampersands are the code implementation of that AND gate. Let's have a quick look then at the OR gate. Okay, now the OR gate is very similar to the AND gate with the exception of the OR. So input A and input B, and then we have one output. Okay, now we're going to swap that AND question for the OR question. So is input A or input B true? Okay, if either of those are true, then the output will be true. The output will actually only ever be false if neither A or B is true. So if they're both false, then the output will be false. Otherwise, the output will be true. If they're both true, it will also output true. Okay, because A or B are true. So the OR gate is very similar to the AND gate, it just changes that logic. Okay, if we have a look at our street lamp and we swap that AND gate for an OR gate, we now have a low light sensor on B, RTC on A, just as before, but now instead of the AND, we have the OR. Let's say that it's 4 p.m. in the afternoon, that a storm comes in, okay, and the low light sensor triggers to say that it's low light. So B goes high, A is low, okay, but it's an OR gate. So is A or B high? Yes, because the low light sensor is high, so the street lamp will turn on in that scenario. It may not be within the time window, but that OR gate is detecting that the light sensor is detecting low light, okay, and so that street lamp will turn on. Let's say it carries on, okay, so the storm carries on and we now get to say 8 p.m. Okay, the RTC is now high, the low light sensor is also high, so is A or B high? Yes, they are, so the street lamp is on. Okay, let's say that the low light sensor, the storm passes over, it's summer, the sun comes back out. Okay, it's 8 p.m. in summer, light is high. Okay, so the low light sensor is going to detect a low signal. Okay, the RTC, however, is still high because it's beyond 7 p.m. So is A or B high? Yes, A is high. Okay, so the street lamp stays on. So by simply swapping out that AND gate for the OR gate, we change the logic of that street lamp. In our code implementation, we can also do the OR. We swap those two ampersands out for two of these down lines. Okay, these are the OR statement. On your keyboard, you'll probably find this on the UK keyboards in the bottom left corner. It probably involves the shift key as well. It does vary based upon your keyboard, so just have a look at your keyboards. That is the key you're looking for in the bottom right there. Okay, so simply by swapping out the IC chip, we can actually change the logic of the street lamp, or simply by swapping out the two ampersands for these two lines, we can actually change the logic in our code as well. Okay. The final gate we're going to look at then is the NOT gate. Now the NOT gate is fairly straightforward. It has one input and one output. It inverts the logic. So if input A is true, it'll invert it so that the output is false. If input A is false, it will invert it so the output is true. So essentially what we're actually doing there is just inverting whatever we put in. It's going to make a true a false and a false a true. Okay. We use this quite commonly in many different circuits just to flip the logic over. Let's have a quick look at an example of a NOT gate. Now we can't actually just plug that straight into our street lamp because our street lamp doesn't require it. Okay, but what we can actually have a look at is that light dependent resistor that makes up that low level light sensor. Okay. First things first, you will notice that the chip layout is exactly the same as the other two. Okay, but now pin number 1 has NC next to it. NC, if you ever see NC on a board or if you ever see it on a chip leg, it means not connected. Okay, they typically leave these on because they want them to be swappable, so you can swap your AND, your OR, and your NOT gates in without having to change your circuit board design. Okay, so NC just means not connected. Just ignore it, don't connect it. Sometimes on the datasheet, it will tell you to plug those into ground. for the most part, you're not going to really come across that, but just bear that in mind. Just read through that data sheet, just see if you should be pulling the NC pins to ground or not. Typically, they're pulled to ground internally. Okay, so they automatically do that inside the chip. Now, what we're going to do is we're going to plug that LDR signal into pin number 2, which is A. And then the output from our low light sensor is going to be coming out of Y. That's going to return either a high or a low. Okay. Now with the LDR, when a bright light touches the LDR, its voltage is going to be high. Okay. And then obviously as it gets darker, that voltage is going to drop. Okay. So when that voltage is high from the LDR, it means there is a bright light touching the LDR. Now we actually want to say, is the light level low? Not is the light level bright. Okay, so what we're going to use is a NOT gate to invert it over. So when the light level is high, it's going to be outputting true from the LDR, but we want to say, is it low light? So we invert it to false. So when the light level is high, we're going to invert it so that is low light is false. When the light level drops, the LDR signal is going to drop to low on pin number 2. Okay, it's going to go through the NOT gate and it's going to invert it. So now that the light level is low on the LDR, it's going to invert it to a true for the is low light level. Okay, so that is low light level sensor gets inverted so that it becomes from a brightness sensor to a low light level sensor. Hopefully that makes some sense. I tried to fit that within the street lamp element. Okay, so hopefully it makes some sense. If not, find me in the class and I will explain it in another way. Okay, it essentially just inverts the logic. Now the code implementation for NOT is actually very straightforward. It is the exclamation mark in front of your value, either your variable or the value itself. So if you say not 40, for example, it's exclamation 40, and that will say it is not 40. If you put it in front of your sensor reading, then it'll be obviously the not of the variable type. Okay, in the case of true or false, it's fairly straightforward. If you have true in your variable, it will come out as false. If you have false in your variable, it will come out as true. Okay, you'll get used to using it over time. Okay, but this exclamation mark is how you make it not. So that covers the 3 basic gates: the AND, OR, and the NOT gate. Okay, now there are other gates out there. Okay, we have the NAND gate, the NOR gate, and the XOR gate. Now the NAND gate is actually a NOT AND gate. Okay, so this is a combination of that NOT gate with an AND gate. So we start off with the AND first, we then pass it into a NOT gate, and then the output from the IC chip would be NOT AND. Okay, NOR is the same, it's a NOT OR gate. So we first pass the signals into the OR gate, we then pass it into a NOT gate, and that outputs NOT OR. Okay, so that will all be done in one chip, so we don't have to have 2 chips to do that. So that's why these NAND and NOR chips exist. The XOR gate is slightly different. It's what we call an exclusive OR. So it uses the X as exclusive. Okay. It works very similar to a normal OR gate, with the exception of that final one. They have to be exclusively true on A or B. Okay. If they are both true, then the output will actually be false. That pretty much covers the basics of different logic gates. There are many other different types out there. Like I say, for the most part, they're combinations of those 3 core gates.